All right, so we just remembered that one of the great powers of grammars is that they can be recursive, just like procedures. You can have a grammar rule that expands to itself, allowing you to have an infinite number of utterances from a finite formal grammar. That gives us a huge amount of power, almost a magical amount of power. But it does mean that we'll need one more element of bookkeeping in order to correctly do parsing. We saw before in one of the quizzes that we could be in a particular state after seeing 2 tokens, 4 tokens, 6 tokens, 8 tokens. So we'll need to keep track of one more number to know which one of those it was. We'll need to know where we came from, or how many tokens we'd seen thus far. So here's a grammar we've seen before. E goes to E plus E, or E goes to int. Our input string is int plus int. And I'm going to start filling out that chart that shows us what parsing states we could be in if we've only seen a subset of the input. So if we've only seen 0 tokens, then we could either be looking for E plus E or we could be looking for int. Those are our 2 grammar rules, but we haven't seen anything yet. There's nothing to the past, everything is to the future. Once we've seen the single int, then we could either be in the middle of parsing E goes to int and we're totally done with it, or if the input is longer, we could be expecting a plus and an E in the future. Here's where things start getting fun. If we've seen the int and the plus, then we could definitely be in the middle of parsing E goes to E plus E, with the dot right here. We've seen 2 things to the left. There's 1 thing in our future. But now we could also start looking for another int. In our entire input, int plus int, we're expecting an int to be the 3rd token. If we saw it, it would reduce, or it would be rewritten from E goes to int. So our current parsing state is we haven't seen it yet, but we're really expecting it in the future. But here's where the potential ambiguity comes in. This state is exactly E goes to dot int. We saw that same state back here in chart position 0. However, they're not exactly the same. This one corresponds to the first int in our input. This one corresponds to the second int in our input. Right? This is what we're thinking about when we haven't seen any tokens yet. This is what we're thinking about when we've seen 2 tokens, but not the 3rd. The parsing rule is similar because the grammar is recursive. It has a small finite structure. But we really need to remember one extra bit of information. When we're thinking about it this time, we've sort of seen 0 tokens so far. Over here, we've seen 2 tokens so far. Or we decided to add this state based on reasoning about state 2. This fact that we could have 2 otherwise identical parse states means we'll need to augment our parse states with one more number of information. We're going to call this new information the starting position or the from position associated with a parse state. One last way to see why we need it. Let's say one of our current states is E goes to dot int, and we actually see that int. It's part of the input. We need to know whether we should go on to sort of chart position 1 and start looking around here, or whether we should go on to chart position 3, which I haven't filled in, and start looking there. We need to know where we came from in order to know where we're going. This is one of the reasons why context-free grammars are more powerful than finite state machines. Finite state machines did not really need to know where they were coming from. They were memoryless in some sense, aside from the current state. We're doing all of this because we want to master parsing. We want to see which strings are in the language of a grammar, to see if HTML or JavaScript is valid before we try to throw it to our web browser's rendering engine. Well, another way to think about this is that parsing is the inverse of producing strings. Rather than producing all the strings in the world, I want to see if this one string could have been produced by our grammar. Over here, I've drawn a little diagram of parsing a simple sentence, int plus int, using our grammar. Well, one way to view this is to think about the parse tree, which I've kind of drawn here upside down. Conceptually, I could apply this E goes to int rule in reverse and rewrite this int with an E, changing the input string so that it has a non-terminal in it. Then I can do the same thing again over here, and now I have E plus E. I can rewrite that to be just E. It's as if I'm taking the rules in the grammar and changing the direction of the arrow. If I view this story this way, we're parsing. Magic trick of perspective. If I read from the bottom up, we're generating or producing strings. Starting with E, I choose to apply E goes to E plus E. I choose to apply E goes to int. I choose to apply E goes to int, and I end up with a string at the end of the day. This way, from the bottom to the top, is generating or producing a string. This way, from the top to the bottom, is parsing a string. applying the reductions in reverse order until you get back to the start symbol. If you could apply all the reductions in reverse order, then you know that the string is in the language of the grammar because you have a script for generating it. Just do everything you did backwards.